Hello and welcome to the Aerospace Ambition Podcast. I'm Kieran, here with my co-host Marius. This show is aimed at sparking important discussions with established experts in aviation, climate science and AI. In today's episode, we're delving into the science behind condensation trails or contrails. These are the line-shaped ice clouds that form behind aircraft, responsible for around 1-2% of global climate impact. Joining us to shed light on this topic is a highly respected contrail researcher, Marius. Can you please introduce our guest for today?
Today we are joined by Dr. Roger Teoh, a visiting researcher with the Imperial College London. Roger completed his PhD in Aviation and the Environment at Imperial College in 2020. His current research interests are on aviation and climate change, with the aim to evaluate and mitigate the climate impact of aviation emissions and Contrail Cirrus. Roger, it's a pleasure to have you on the show.
Thank you for the opportunity, Marius and Kieran.
Great to have you.
So Roger, you're a research associate at Imperial College London, and I'd say pretty highly regarded in the field of aviation climate science. So could you give us a brief summary of your academic journey in recent years, and have you always been a contrail researcher?
Well, thanks for the question, Kieran. Yes, so I went to Imperial in 2015 to pursue my master's in transport studies. So during that time, the syllabus covers a wide range of topics, including aviation and trains, simulating traffic flow. But it's in particular it is the aviation module that sparked my curiosity and interest in this topic. So because of that, then I started to apply to further my research and apply for a PhD in aviation and the environment. And yes, there was one lecture from Dr. Mark Stadler that looked into contrails. And from then, we started writing the proposal. And so I started my PhD in 2016. We took a step back. We look at the aircraft particle emissions before contrails, because as we will discuss about in the episode later, these particles they can strongly influence the young contrail properties. So once we have an improved model on simulating the aircraft particle emissions, we then integrate this into the contrail model that we are using right now. So that was between 2016 to 2020. From then onwards, once I finished my PhD, I spent about 6 months in industry, not related, but it was finance. But I felt that, I still feel that there's still a lot of unfinished business that I need to continue my work on. And I rejoined Imperial in, when was it? June 2021. And I was there since, all the way until today.
That's a very strong inner calling, right? There was unfinished business, and that then drove your passion to come back. And yet, would you recommend all researchers maybe to spend some time in the industry to also maybe not only have the technical view on the problems, but maybe this completes your view, right? To also look at it from a commercial point of view. Did it also help you in regarding contrail management or the contrail problem and how it could be implemented?
I've learned a lot of statistics in finance that could be applied into analyzing contrails. Because as we know, as we will talk about later, there are a lot of uncertainties involved in contrails. So again, it's the same as like managing risk in the financial markets.
So before we dive right into the real technicalities of uncertainties and the science, I think it's good to maybe just start off with some of the basics on exactly what contrails are. So we know by now that contrails have a fairly significant impact on the climate, and they're thought to primarily warm the climate. However, on a contrail by contrail basis, the formation, the lifetime and the persistence of a contrail, and finally its climate impact are largely dependent on the operational conditions of the engine, as well as the thermodynamic conditions of the atmosphere, in which the emissions are released into. So can you give us a rundown on exactly what a contrail is? So what emissions cause it, the physical processes that result in ice crystal formation, as well as why they contribute to climate change?
Sure. Yeah, thanks, Kieran. So in short, when you burn fossil fuels by aircraft gas turbine engines, you would release water vapor emissions, and you would also release soot particles due to incomplete combustion. So contrails form when conditions in the exhaust plume is supersaturated with respect to water. So in other words, that's when their relative humidity exceeds 100%. So when the exhaust plume cools from the exhaust temperature all the way down to the ambient temperature, that's where you get an increase in the relative humidity in the exhaust plume. So if the relative humidity is above 100%, this would allow the water droplets to condense onto the surface of the soot particles, and then they start to freeze to form contrail ice crystals. So I'd like to make this clear, is that this process is related to short-lived contrails. So the conditions in the exhaust plume, it does not mean that the contrails will be persistent. So in order for contrails to be persistent, the ambient atmosphere needs to be supersaturated with respect to ice. And based on our statistics, around 75% of all contrails are short-lived. So meaning that they sublimate within 2 minutes after they form, because the atmosphere is not supersaturated with respect to ice. And the remaining, so only about 25% of the contrails are persistent, meaning that they survive for more than 5 minutes. For these persistent contrails, they can spread over time and cover a large area.
And grow over time as well, yeah?
Yes, they grow over time, they mix with natural cirrus, and it could cover up to 10% of the sky area in high air traffic density regions such as Europe and the US. So because you have a layer of clouds, in general, you change the radiative balance on the top of the atmosphere. So during the day, contrails can reflect incoming solar radiation back to space and cause a cooling effect. But during the night and at all times, even during the day, it also traps the outgoing long-wave radiation and re-emits it back to the surface, and that causes a warming effect. So as you know, Marius and Kieran, based on the science, we can agree that contrails, the climate forcing from contrails is generally net warming. And 1 year of the global annual contrail climate forcing could be around 2 times more than the climate forcing from aviation's cumulative CO2 that has been emitted since the 1940s.
So not a small contribution we're talking about here. So 1 year of contrail forcing is twice the amount of warming as all of the CO2 emissions released from aviation since 1940. Is that what you're saying?
Yes, but again, there's a caveat that the uncertainty bar remains huge.
Okay, yeah.
So on average, the latest results show that it's about twice, but there are other earlier studies that found it to be larger. But we can talk about in this later in the call on this discussion on like why there is a discrepancy between our recent study and earlier studies.
The climate impact of individual contrails is largely dependent on whether, of course, the contrail will form or not. Then if it does form, how long it persists in the atmosphere for, and whether it sublimates over time, like you said, a short-lived contrail, or whether it grows over time by taking up the surrounding water vapor in the atmosphere. And then finally on its radiative forcing, which is the instantaneous climate impact of a contrail. And this largely depends on the microphysical properties of the ice crystals and whether it's daytime or not. And of course, this is a measure of exactly how much impact this contrail has on the climate. So could you expand on some more of these factors which maybe come from the conditions of the engine or the conditions of the atmosphere, the spatio-temporal factors which affect contrail formation, persistence, and climate impact?
That's a very good question. So if I were to summarize this question, like you're asking about what are the main factors that influence the contrail climate forcing. So, well, based on, in my opinion, there are about 4 main factors that influences the contrail climate forcing. The first one is the diurnal effects, as we've talked about earlier. So during the day, contrails can be cooling, but it does not mean that it will be cooling. There is a possibility that it will be cooling. And during the night, it is always warming. So that's clear. The second factor is the seasonal effects. So because let's use the northern hemisphere as an example, because 92% of all the air traffic globally occurs in the northern hemisphere. So in wintertime, you don't get a lot of sunlight. The hours in a day is shorter. Therefore, and nighttime is longer. And for these reasons, contrails tend to be more warming during the winter. At the same time, in the winter, the atmosphere is also colder. Therefore, you tend to form slightly more contrails, persistent contrails, relative to the summer. So that's the second factor, the seasonal effects. The third factor is the aircraft particle emissions. So as we talked about earlier, the water vapor that's emitted by the aircraft engine and the ambient water vapor needs to condense onto a surface in order for it to form water droplets. So based on current aircraft engine technologies, there's still a lot of soot and non-volatile particulate matter that's present in the aircraft exhaust. So for this case, for today, the soot particles that are emitted by the engine plays a big role in determining the lifetime of the contrail and the climate forcing. So if I were to elaborate this further, imagine if you have a fixed amount of humidity in the atmosphere. If you emit less soot particles, then the ice crystals would be larger because the fixed ambient humidity is distributed to less particles. Therefore, each particle will get more water vapor and more water content. If the ice particles are larger, they sediment down. They can sediment at a quicker rate. And because of the higher sedimentation rate, the lifetime of the contrails would reduce. Because the lifetime is reduced, they don't have enough time to spread to a large area, and therefore you reduce the contrail climate forcing. So to summarize, less particles would generally lead to less contrail climate forcing. That's the third factor. The final factor is the background cloud, the background radiation. So imagine if you're at Southeast Asia, it's in the tropics, you receive a lot of incoming solar radiation. Because of that, the contrail shortwave radiative forcing, you're able to reflect more solar radiation back to space. Whereas if you're at the Arctic, well, you get less solar direct radiation, and therefore you reduce the magnitude of the shortwave radiative forcing. The other component is the outgoing longwave radiation. Think about the Sahara Desert. There's no clouds. The surface temperature is very warm. So you get a lot of outgoing longwave radiative forcing that's going to hit the contrail. Because of that, you increase the longwave radiative forcing from the contrails. So where the contrails form and its radiation characteristics is also a factor influencing its climate forcing.
So would it be deserts and over large areas of ice, because you've got high albedo from the ice as well? So a lot of reflectance from the surface of the ice layers will mean that there's a lot of outgoing radiation. And probably in the Arctic or like in these polar regions, you've got a lot less inbound sunlight. So it's only typically a lot of outgoing radiation compared to incoming solar radiation. So that would generally be a much larger warming effect compared to if you were flying over a populated region.
Yes, Kieran. So that's approximately right. So essentially the short wave and long wave radiation. So the short wave radiation affects the cooling effect of the contrails, whereas the long wave affects the warming effect. So these two, the short wave and long wave radiation, have different wavelengths. So if you're at the poles, the surface is white because of the snow. The poles would naturally reflect the incoming solar radiation, even if you don't form a contrails. So it doesn't really, if you include the contrail on top, well, the solar radiation has already been reflected by the surface, so there's not much that the contrail could do.
So we've just learned about 4 of the major factors influencing the contrail climate forcing. And in the previous conversation, we've learned about the concerns of airlines when it comes to mitigating non-CO2 climate effects. And what Dr. Alejandro Bloch underlined was that it would help massively for regulation and policy making if we could better understand, of course, the non-CO2 climate impacts, and if we could quantify them better. So right now, talking about uncertainty, what are the biggest sources of uncertainty in contrail science at the moment?
I'll list 3 or 4 of the major uncertainties. There are a lot more uncertainties in that, but yeah, let's focus on the biggest uncertainties. The first biggest uncertainty is the meteorological forecast. And because in order for us to forecast the contrails, we need to use a numerical weather prediction model. So if we look at the state-of-the-art ERA 5 high resolution realization, HRES, from the European Center for Medium Range Weather Forecast, at its current form that's publicly available, the current 4D spatial temporal resolution, it's about the spatial temporal resolution is about 0.25 times 0.25 degrees longitude and latitude over 37 pressure levels and at an hourly time interval. So at the moment, there is not enough horizontal and vertical levels to capture the subgrid scale variability in the ice supersaturated regions. So that's one factor. The other factor is that there are limitations in the ERA 5 HRES because of simplifying assumptions. So in the RHI, the relative humidity with respect to ice that's provided by these numerical weather prediction models, they tend to be weakly supersaturated. So they tend to range between 100 to 110% RHI. But based on the measurements that we see, the RHI, the relative humidity with respect to ice, could be as large as 140 up to 160% at very localized regions. So we need to account for that. The second uncertainty is the shape of the ice crystals. So the contrail ice crystals could be a sphere, it could be plates, it could be rosettes or columns. And these have different properties in influencing the short wave and long wave radiative forcing for the contrails. Of course, we have experimental campaigns, chase planes that went up to sample the contrails. But again, these are generally young contrails. So we don't have any observations or any real world data to see how does the contrail shape, ice crystal shape evolve over time. That's an uncertainty. We also have the role of the volatile particulate matter in contributing to the contrail ice crystals. So if you remember earlier in the talk, we mentioned that at present day, we assume that the contrail ice crystals are formed by condensers. The water vapor condenses onto the surface of soot particles. So that's the NVP, the non-volatile particulate matter. However, there are some evidence that for cleaner engines, and if you're using 100% SAF, when there's no soot particles present, the contrails, the water vapor could condense onto the volatile particulate matter, such as sulfuric acid, lubrication oil, and organic compounds. So again, that could influence the number of ice crystals in the contrails, which then influence the lifetime and the climate forcing. So that's the third uncertainty. So the final uncertainty is the second order effects. So if you form a contrail, because it's competing with it's dehydrating the atmosphere because it's competing with the water vapor with the natural cirrus clouds. How does it reduce the natural cirrus occurrence? And how does it change the properties of the natural cirrus? So these are uncertainties that are unknown.
What do we know about, for example, one flight goes through an ISSR area, right? And consumes, let's say, to some degree the water vapor that is in that area and forms a contrail. So what do we know about then a second or third, flight that goes through that area?
Yes. Okay. So if we look at this based on one study that was conducted by Ulrich Schumann from the German Aerospace Center in 2015. So what he did was he coupled the contrail model with with a climate chemistry model. In essence, okay, if you form a contrail, the atmosphere gets slightly dehydrated. If you form a second contrail, there's less water vapor in the atmosphere. Therefore, the ice crystals would be smaller. If the ice crystals are smaller, the sedimentation rate is lower, so it could increase the lifetime. And again, because it increases its lifetime, it has more time to spread, and that could increase the contrail climate forcing. So this does not account for the changes in natural cirrus, but based on this study, on average, if you account for these effects, dehydration of the atmosphere, you could increase the contrail net radiative forcing by about 10 to 20%.
Another aspect of, we're talking a lot about these uncertainties. I know, of course, you ask an expert about uncertainties, you will get a lot of answers about that, right? So we are now highlighting only the uncertainties. I think it's important to mention. Another point that may be raised by people who are opposed the immediate implementation of contrail mitigation may be that we don't know about the counterfactual scenario. So let's say we predict that there is an ISSI area, we divert flight, but we don't actually know what happens to that area now. Like, what are we comparing this diversion to? Would a Contrail Cirrus have formed anyways, and what would have been or would be the climate impact of that? How would you comment on that?
Yeah, that's a very difficult question to answer. It's very challenging. So I think the best solution to this is to divert perhaps half of the flights around the ice supersaturated regions, and half would remain the status quo, and then perform some statistical analysis by looking at the satellite observations to see if contrails formed at the area and at the region where we predict it to be strongly warming contrails.
Yeah, I think that's a fair comment. And I remember hearing from an expert in the field say that, so when we carry out these operational trials, instead of doing trials to avoid contrails, we should actually do the counterfactual of that and look to explore contrail trials which seek out the formation of contrails and to see just how many we can create with enough certainty, and to model their climate impact and see if it's the same as what we predicted. So maybe this is something for the near future for us to really capitalize on those gains in terms of what we know about contrails now and to make sure that we're predicting them right. And I think this nicely rounds off the discussion on contrail science to talk about your latest paper on the global climate effects of contrails. So in this paper, you discovered that the radiative forcing of contrails may actually be overestimated, or at least to the best estimates. Of course, the error bars are still very large, but you gave a refined estimate which was towards the lower end of the error bars. So, and this is compared to the David Lee 2021 paper. So could you maybe outline the key differences in your approach, your methodology, and the relevance of this study in our pursuit for rapid mitigation of contrail warming?
Thank you, Kieran. So before I start discussing about the results, I would like to have a caveat. Just mention a caveat here. Said, yeah, all models are wrong, but some can be useful. So of course, like the models that we use, the Contrail Cirrus prediction model, CoCiP, that was developed by the German Aerospace Center, has limitations as well. So it does not account for the second order effects and how does the contrails influence the natural cirrus formation. And we recently started implementing the contrail overlapping effects. And the third thing is that we do not account for the dehydration of the atmosphere. So these are some of the limitations in our model. But essentially what we found was that actually the global annual mean Contrail Cirrus net radiative forcing in 2019 is about 62 milliwatts per meter square. And that's about half of that of the current best estimates from David Lee's paper, which is 101 milliwatts per meter square. So what we found in our paper is that the percentage of flight distance forming persistent contrails, they are different at different regions of the world. So we found that actually in the subtropics, so it's plus or minus 30 degrees north and south, you don't tend to get a lot of persistent contrails forming at the subtropics. One of the reasons is because of what we think is the main reason is because of the Hadley circulation. So if you know, warm air rises from the equator. So rising air mass, like persistent contrails tend to form in rising air masses because of adiabatic cooling, which tends to facilitate the formation of ice supersaturated regions. But as the air, as you get a convection of the air from the tropics, and by the time the air reaches the subtropics, it tends to be dry. It's drier. And the air would also sink down to the surface at the subtropics. Because you get adiabatic heating from the sinking of the air mass, you get less ice supersaturated regions in the subtropics.
And less contrails, yeah.
But in David Lee's paper, what he did was he compiled the results. I think it's about 3 or 4 results that simulated contrails globally for 2006. So you get he got an RF. Well, the team got an RF, a radiative forcing estimates for 2006, but he scaled the contrail radiative forcing up from 2006 to 2018, assuming that the contrail radiative forcing is proportional to the growth in global air traffic. But as you and I, we know that between 2006 and 2018, most of the air traffic growth occurred in China and India. And in these regions, there's not as much persistent contrails forming. Therefore, you don't get a proportional effect in terms of the contrail radiative forcing.
What about the altitudes? Was that also another factor in the paper? So one being the subtropics, Hadley circulation that you just pointed out. But isn't there also this other aspect that in China, there are different cruising altitudes?
Yes, that's a good observation, Marius. So what we found based on the ADS-B data, so that's automatic dependent surveillance broadcast. So aircraft are mandated to broadcast their position, their 4D position, twice a second. So based on these ADS-B data, we see that actually like flights over China tends to fly at lower cruising altitudes relative to the rest of the world. It's most likely due to the airspace structure, because there was one study that mentioned that about 70 to 80% of the airspace is reserved for military use. So when you compare that to the United States, if I got the figures correctly, it's about 10 to 20% of the airspace that's reserved for military. So what that means is that the commercial air traffic would need to fly at lower altitudes. That's the airspace structure. And yeah, that by lowering the altitude, you could also contribute to less persistent contrails forming.
But doesn't that also imply that you're generally flying less efficiently?
Yes, that's right. So what we saw, there was another paper that we will talk about, I guess, later. We looked at the global air traffic activity in 2019. We see that the lateral inefficiency, so that's the additional distance flown relative to the Great Circle distance between the origin and destination airport, it tends to be higher for China. I think it's it's about 10%, if I got the figures right, relative to the US, which is about 3 to 4%. And over Europe, it's about 6 to 7%. So the lateral inefficiency over China tends to be higher at about 10%. So again, you're burning more fuel and CO2 emissions as well.
This is crazy. You've just mentioned that 70 to 80% in China is reserved for the military. And this results in, a different airspace structure, which has concrete impacts on contrail formation. Now, in the US, you said 10 to 20%. So basically the opposite, one may say, right? And with all the political stuff going on in the world right now, militarization, all of that, especially around the Ukraine right now, this is a glass bowl thing, crystal ball thing. But when you look in the future and there are more military things going on, how do you see the correlation then potentially or the impact potentially for contrail formation? For example, if you assume that now in other regions of the Earth, it will turn, towards this 70, 80% for military.
So first of all, I think, I could be wrong. I think that the airspace, that the reservation of the airspace over China, it's mainly for training purposes. Whereas if you look at the problems that we are facing today, is that Western countries are actively avoiding the Russian airspace and the Ukrainian airspace, and that would increase the lateral inefficiency. But how does it impact the contrails? Well, we have not done a study on it, so I can't really comment on how the contrail climate effects change. But I would assume that it's probably higher because you're burning more fuel, you're emitting more particles, and again, there's more probability for the aircraft to fly into isopersaturated regions because you're flying longer distances.
Yeah, so I think this can lead on to the section where we talk about contrail mitigation, because with increased militarization, like we've been talking about, and the blocking of airspace due to conflict regions and to military training, this leaves obviously a lot less airspace to play with in terms of avoiding isopersaturated regions where you might form persistent contrails. So measuring and modelling contrail climate impact is clearly a much more complex issue compared to that of CO2 emissions and the climate impact of those, because CO2 is a relatively inert greenhouse gas. It lasts in the atmosphere for potentially hundreds of years and has a more gradual warming effect, whereas with contrails, they have a much more localized and short-term effect. And of course, as we spoke about previously, there's a lot of spatio-temporal dependence, meaning that depending on when and where you're flying, the contrail may have a completely different climate impact, or it may not form altogether. So due to this, of course, it massively increases the complexity of the issue and the modelling. However, it does open doors to new mitigation methods. So we can apply different methods to reduce contrail warming compared to if we wish to reduce CO2 warming. So what would you outline as the key mitigation methods that we have at our disposal, or at least may do in the near future, to really reduce contrail warming in the interim to truly low or zero carbon flight?
Thank you, Kieran. That's a very good question. Before I answer the question, I would like to just add some corrections.
Sure.
So I think this is where most of the people, I guess, I can't say it's wrong, but perhaps we need to change our mindset. The main point is that we should not avoid the formation of all contrails. We only need to minimize the formation of strongly warming contrails. Because again, as we've discussed earlier, 75% of the contrails are short-lived, and 25% of them are persistent. And out of this subset of persistent contrails, 30% of the persistent contrails have a net cooling effect. And you would say that maybe 50-60% of the warming contrails, they're just slightly warming. So to give you a statistic, based on our global study, around 2 to 3% of all flights account for 80% of the contrail energy forcing. So that would somewhat make our lives easier, because we can focus on the subset of flights that are producing strongly warming contrails. So by doing that, we would minimize the disruptions to air traffic management if we were to divert the flights to minimize the formation of strongly warming contrails. So again, the first option would be to perform flight diversions to minimize strongly warming contrails, but there are advantages and limitations to it. The second option is to use sustainable aviation fuel, and because SAF, sustainable aviation fuel, it impacts the contrail formation and climate forcing in two different ways. If you use sustainable aviation fuel, because the hydrogen mass content is higher, you would increase the water vapor emissions index. Therefore, you increase the contrail occurrence slightly by about 1 to 5%. But because you're emitting more water vapor, and you are also emitting less soot particles, because SAF contains much less aromatic content, so that reduces the amount of soot particles that you're emitting. Less particles, more water vapor emissions. You lead to forming, so the contrail ice crystals would be larger, and that can reduce the contrail lifetime and climate forcing if you use sustainable aviation fuel. But again, there are advantages and drawbacks to these two options.
So only 2 to 3% of the flights make up for the majority of the warming, right? That comes from contrails. Now, operationally, I totally agree. I think it's a no-brainer that operationally this will be much easier than to implement if there are only, you can be much more effective, and in basically avoiding this impact. Now, when it comes to regulation or actually implementing this and incentivizing airlines to act, I'm thinking, doesn't this mean that there's one airline and one flight that is like super unlucky because that happens to be the big hitter at that day, right? And now they have to maybe take into account a fuel penalty. So how would you comment on maybe really the regulatory implementation of, avoiding big hitters?
So, okay, Marius. So to clarify, it is likely that when a big hit, when there are regions with strongly warming contrails forming, it would likely affect a fleet of aircraft rather than one specific flight, one unlucky flight. So it's likely that at one particular day and at a particular place in time, you identify the region that would form strongly warming contrails, and then you might need to do something to perform mitigation actions on a subset of affected flights, not just one flight. So again, there are uncertainties involved in this, but we hope that if you focus on the fleet instead of individual aircraft types, we hope that the errors would cancel each other out. And by doing this diversion over a fleet of aircraft, you would reduce. You hope to get a net climate benefit after accounting for the uncertainties and the errors in our meteorological forecast.
But we've talked about the geographical and temporal inconsistencies of contrail formation and contrail climate impact. And also when you think about air traffic flows, there's going to be inhomogeneity there. So when you've got different airlines flying different routes, maybe different times of the day, this may lead to a certain bias towards a particular airline, which may have to take a lot of that hit in terms of rerouting the flights and increasing fuel penalty. So how do we go about mitigating that?
Well, this is a policy question, but I can provide my opinion as well. So let's say if we were to monetize the potential increase in fuel penalty and operational cost associated with diverting flights, we could set up a pot where the travelers you could have a levy on the ticket prices, and that would go to a common fund, and you would provide the fund and allocate it to the flights that are expected to form strongly warming contrails. But again, spread the benefits. The benefits would be equally shared.
Alejandro asked a question. We have this tradition of passing on a question from one guest to the next. So he knew you were coming on, and he passed on the following question. How does the uncertainty of radiative forcing of fleets compare with individual flights?
Based on our study, there was a 2020 study, we looked at the uncertainty on a fleet level and the uncertainty for individual flights. And not surprising, the uncertainty, even if you pick one flight that has strongly warming contrails, there is a very, very tiny possibility, well, less than 10%, that the strongly warming contrail could actually turn out to be cooling for that one flight. But if you look at a fleet level approach and you target a subset of flights that are expected to form strongly warming contrails, you would get false positives and false negatives. But we hope, and I think it will, the errors will cancel out. And therefore, we hope that by looking at the fleet level, you get a net climate benefit if you focus on the uncertainties at the fleet level.
Yeah, because it's, especially when you're thinking about an individual flight, taking that flight from the trajectory that it flies to then estimating the fuel that it's burning, so the aircraft performance, then to estimating the emissions that it's releasing throughout flight. Once you've got the emissions, you need to know the meteorological conditions in which it's flying through. That will then determine whether a contrail will form or not. If the contrail does form, is it going to be persistent? Is it going to be short-lived? If it's persistent, what's its climate impact? Then you have to analyze the optical properties of the ice crystals. Only then can you start to think about how much of an impact that has on the climate. So we can look at radiative forcing, which is an instantaneous measure, and that only measures what's happening in the here and now. But then you got to think about how does that integrate over time. So there's so many steps along the way where we can go wrong, from thinking about, okay, we have a flight. What is the actual surface temperature change that results from this particular flight? And it's going to be obviously a tiny number. So that's obviously a lot different of a problem compared to if you're measuring the global radiative forcing from all contrails. And yeah, I just wanted to make that statement clear that it's clearly two very different problems that we're dealing with, and measuring the climate impact of individual flights is going to be a much more difficult problem.
I think this summary was really helpful, Kieran. And this leads to the next point, something we could do in mitigating contrails, and that is using SAF in a more targeted way. You've conducted a SAF study, and I'm curious, what are the key findings of the study, and what is a risk with implementing this method? Maybe you can explain to our audience what the results were.
Sure. Thanks, Marius. So, okay, we know today one of the limitations that the world is facing is that we do not have enough SAF supply. So, for example, in 2023, I think SAF only accounted for 0.2% of the global aviation fuel consumption. It is way too low. But what we came up with in this study, this 2022 study, is that what if we target the scarce supply of SAF? So essentially, we blend the SAF at a higher blending ratio and target it to flights that are expected to form strongly warming contrails. So if we do this, due to the different processes that we spoke about and on how SAF would influence the contrail climate forcing, we could actually increase the net climate benefits by effects of 5 to 10 if we perform this targeting. Again, what are the caveats? The caveats is that the forecast has to be accurate, but even if we get the forecast wrong, it's okay, because we have a co-benefit, because SAF should also reduce the CO2 life cycle emissions. So therefore, you have some margin of error. The second point that we are focusing on right now in a separate study, still ongoing, is that how if we need to perform this targeting of SAF, that means that the SAF needs to be separated from conventional fuel and stored and only used when it is necessary. So how does that affect the supply chain at the airports? Would there be any additional cost involved in it? So yeah, we're still looking into it, and we hope to present our results in a couple of months.
Do you think that the discussion right now, or that people are aware that the use of SAF has such a strong connection to contrails?
In my opinion, not yet. But again, there is a mandate by the European Union, the UK, and just 2 weeks ago, Singapore joined in as well. So they are mandating the use of sustainable aviation fuel. So starting from 2026, at least for Singapore, all flights that are departing from the country has to use fuel that is blended with 1% SAF. So okay, we are trying to facilitate the use of SAF. So again, there exists this opportunity where we could use the SAF more efficiently. But at the moment, I don't think it's being looked at. But again, yeah, that presents opportunity.
Yeah, so I think there's one final area of uncertainty which we haven't really covered when it comes to implementing SAF for this purpose, to reduce contrail formation, and that's the topic of uncertainties in aerosol cloud interactions. So there's a lot of science that we probably don't really know about yet, which is looking into how aerosols interact with clouds and how they may interfere with the natural processes that occur in this area. And so I think that leads us on to our final part of this discussion, and that's something more generic, looking into the climate modelling of aviation and your emissions inventory, which you published just last year. So you collaborate a lot with Breakthrough Energy in the US, and you're very active in utilising the PyContrails open source repository, which we've spoken about in a previous episode. So can you tell us a bit about how you might have contributed to this repository in terms of what models you've added and how you've used PyContrails in your research?
Yeah, thank you, Kieran. So essentially, what I've done, like my role on the PyContrails repository, would be to write codes to open source and improve existing models that are used to estimate the aircraft performance in terms of the fuel consumption, the overall efficiency, as well as the emissions, the CO2 and the non-CO2 emissions, such as nitrogen oxide, NOx, and NVPM, the non-volatile particulate matter emissions, which is important for contrails. And what we've also done, the crown jewel of the PyContrails repository is the CoCiP Contrail model. So that's developed by the German Aerospace Center. So previously it was coded up in Fortran. And what I've done during my PhD was that I recoded it up in MATLAB. But again, MATLAB is not used as much relative to Python. So for this collaboration with Breakthrough Energy, we again recoded CoCiP into Python to simulate, so that simulates the formation, evolution, and climate forcing of the contrails.
Okay, yeah. So this, of course, is what you've used a lot of PyContrails related models to develop your new aviation emissions inventory, which is the Gaia dataset. Can you elaborate on what this dataset is and how researchers can apply it?
Yeah, sure. Thank you, Kieran. So the new global aviation emissions inventory, so it is based on ADS-B, the automatic dependent surveillance broadcast, ADS-B telemetry. So we name it as Gaia, Gaia. So it's again global aviation emissions inventory based on ADS-B. So it contains data on the global air traffic activity and the CO2 and non-CO2 emissions for 2019 to 2021. So it is an improvement relative to existing global aviation emissions inventory because previous inventories were based in 2006 and only the aircraft activity in the US and Europe are based on actual flight trajectories. Everything outside was assumed to, like the aircraft was assumed to fly a great circle distance because there was no radar coverage. Well, there is radar coverage, but the data was not shared. So our inventory uses ADS-B telemetry. So that allows us to know the exact position of the aircraft, even in remote regions that previously lacked radar coverage, such as the oceans, the deserts, and very remote regions. And so we hope that with the use of this ADS-B data, we can have more accurate flight trajectories, which can then be used to simulate the climate impacts of nitrogen oxides, NOx, and contrails, because these two pollutants are very spatial temporal. They have a very strong spatial temporal dependence in terms of the climate forcing. So we've open sourced this data set, so it can be used by researchers around the world. It is about 300 gigabytes. You can find it at Zenodo. So we hope that if different models, such as the CoCiP Contrail model, which is a Lagrangian model, and general circulation models, which is used by other research groups, if we can use the same input parameters and then improve input parameters, we could then perform intermodal comparisons to understand the uncertainties in the control climate forcing and other NOx factors.
Yeah, so correct me if I'm wrong, but this data set is at a much higher resolution than your typical climate model. So is it 0.05 degrees resolution laterally, which is, I mean, the chemistry model that I use on a daily basis it's got a resolution of 5 degrees by 5 degrees. So going from 5 degrees to 0.05 degrees, that's a massive step change in resolution there. And hopefully will mean that we can much more accurately quantify these small scale effects or the subgrid scale processes.
That's right, Kieran. So in essence, we're trying to future-proof the Gaia dataset. And again, it can be applied to different studies with different objectives. So for example, if your general circulation model has a global nature, you could aggregate the data into larger grid cells. Or at the same time, on the other hand, if you want to look at the local effects of the contrails or the NOx, you could use the very high spatial temporal resolution and focus on a specific region. So again, there's flexibility, and we are future-proofing it.
And what's next to come from you, Roger? What can we expect in the pipeline in terms of your upcoming research and maybe upcoming papers as well?
That's a very good question. So essentially, what I'm doing right now, I'm focusing on collaborating with Breakthrough Energy. So we are working on a contrail forecasting tool. in order to identify regions that are expected to form strongly warming contrails. And if we want to include some uncertainty in it as well, so we would eliminate those grid cells where we think that actually the uncertainty is too large, so it's not worth doing any contrail mitigation. So again, focusing on cases where we are highly confident that it is a strongly warming contrail, and we are going to provide these information, the 4D contrail forecast, to flight planners in the hope that so it will be integrated into the workflow and systems of flight planners, so it can be used in the real world.
And how is this different from what is already in PyContrails and what, for example, FlightKeys is doing also with Breakthrough and you involved?
Yes. So what FlightKeys has is essentially a prototype of this contrail forecasting tool. But again, we're in the process of improving it. And if you were to look at I guess your question is, what is the difference between the CoCiP that is already in PyContrails relative to the contrail forecasting tool? So in PyContrails, the existing CoCiP is a trajectory-based CoCiP. So you simulate contrails at each flight segment along the flight trajectory, whereas this contrail forecasting tool gives a 4D map of the regions where we are expecting to form strongly warming contrails. So essentially, it's something similar to turbulence. We want to know which region that we are expecting to have to form strongly warming contrails, and perform some mitigation actions to perhaps reroute around the region that we are highly confident that they are going to be strongly warming contrails.
So I guess the key difference is that you've got CoCiP, which is the Contrail Cirrus prediction model, which is in a way a backward-looking model because you're looking at a trajectory and of course you're forecasting whether it's going to form a contrail or not, but you could run a load of different trajectories and do a load of different runs, but it sounds like this new model is much more a forward-looking model where you've got a whole map of airspace and you can see directly what regions would be best to fly through in terms of minimizing strongly warming contrails.
That's right, Kieran. So with the existing trajectory-based CoCiP, it is very computationally intensive to optimize the flight trajectories because you have to just try different iterations. Whereas if, on the other hand, with this contrail forecasting map, you have a map, so you are able to know where the strongly warming contrails are and feed this information as a cost function so that the optimizer can find the most optimal trajectory.
I have to make a cut here. This all you've just explained is a very, very important contribution to getting the industry to more certainty and solving some of the concrete problems in operationalizing it that we have. Now, let's take, at the end of this episode, let's take one step back. There is such a broad spectrum of solutions when it comes to sustainable aviation. We've touched upon a couple of them. But of course, the spectrum also includes to reduce flying, for example, in any way, by any means, just on a high level. How do you view this spectrum? And maybe on what end are you?
So, in my opinion, this is a societal question. So everyone is entitled to have their own opinions. My opinion, I don't think we should stop people from flying, because essentially there are three elements in the definition of sustainability. You have the economic effects, social impact, and the environmental impact. Of course, we know that there's a lot of negative externalities from aviation, but it needs to be balanced against its socioeconomic benefits. To be honest, aviation is currently not on track to meet its 2015 net zero objectives. But again, it has to be weighted with the socioeconomic benefits that it has.
Thanks for providing that opinion, and opinions are very important, especially when it comes to experts like you. And in light of the next expert that we have, of course, you will also have the opportunity to pass on a question. And you gave a keyword already, and that is wake experiments. You mentioned it very briefly at some point in the discussion. And the next guest that we'll have on is an engineer from NASA, Dr. Roger Teoh, who is basically very deeply involved in those experiments, also together with the German Aerospace Center. What could be an interesting question to ask him?
Yes, that's a very very important guess that you have. So, Professor Richmore, I really like your work. You produced a lot of cruise measurements that are important. You measured the soot particles and the contrail properties at cruising altitude. So I guess you're working on this right now, but we are very excited and keen to see, look at your most recent results, where you measured the contrails and contrails ice crystals that were formed by the next generation engines, the cleaner lean burn engines. So these are the soot poor conditions where volatile particulate matter could contribute to the contrail ice crystal formation. So can you talk more about the results? Are you seeing that volatiles and what type of volatile particulate matter is contributing to the contrail ice crystals?
He will love that question for sure. Thanks a lot for that, Roger.
Truly from one scientist to another that question.
Roger, thanks so much for taking the time. And we'll definitely stay tuned with all the work that you've been alluding to. Other than that, we just say thank you.
Yes, thanks a lot, Roger. It's been a really, really interesting conversation.
Thank you for the opportunity.
Thank you, Roger. Bye-bye.
Bye.